Today we have the double integral from 0 to pi by 4 of log tangent x plus tangent y dx dy. Okay, cool. So how exactly should we begin the solution development? Well, it makes logical sense to first expand the tangent functions, so let's go with that. We have the double integral over the region 0 to pi by 4 squared that I'm just going to call d here of log. Let's see, we have sine x divided by cosine x plus sine y divided by cosine y dx dy. And we can play around with the argument of the logarithm function. So we have the double integral over the region d of log sine x times cosine y plus cosine x sine y divided by cosine x times cosine y dx dy. Now in the numerator, notice that what we have is exactly what sine of x plus y looks like. So we're going to make use of this plus the properties of the logarithm. So we can express this as the difference of two logarithms. And we have the double integral over d of log sine of x plus y minus log cosine x times cosine y. And of course, this can be expanded further. You would have log cosine x plus log cosine y, and because of the negative sign in the expansion, we have log cosine x minus log cosine y dx dy. Now, to make use of the linearity of the integration operator, we have I being equal to the double integral over d of log sine x plus y minus the integral over d of log cosine x dx dy minus the integral over d of log cosine y dx dy. Now, the entire solution development for this integral is pretty much based on symmetry. So let me divert your attention to these two integrals here. First up, notice that we have the double integral from 0 to pi by 4 of log cosine x dx dy. By symmetry, this should be equal to the double integral from 0 to pi by 4 of log cosine y dx dy. In both cases, we see that we have a function of x and no function of y, or a function of y and no function of x, depending on whatever way you want to see it. So we could declare this equal to the integral from 0 to pi by 4 of log cosine x dx times the integral from 0 to pi by 4 of dy. So that means all we have here is pi by 4, and that's the result for both these integrals, meaning that the target integral I equals the double integral from 0 to pi by 4 of log sine x plus y dx dy minus twice this integral, which means we have pi by 2 times the integral from 0 to pi by 4 of log cosine x dx. Now let's try reducing this integral here into a nicer form by isolating it as I sub 1. So I sub 1 defined as integral 0 to pi by 4, integral 0 to pi by 4, log sine x plus y dx dy. We're integrating first with respect to x and then with respect to y. So let's adopt an integration by parts approach, whereby we have the integral from 0 to pi by 4 of x times log sine x plus y, where the limits here are 0 and pi by 4, minus the integral from 0 to pi by 4 of x. Now, differentiating log sine of x plus y gives us sine of x plus y in the denominator, and upstairs we have cosine x plus y now, dx, and we also have the entire thing being integrated with respect to y. So applying the limits to the first term, we have integral 0 to pi by 4 times log pi by 4 plus y. Wait, terribly sorry about that. It's sine of pi by 4 plus y minus in the limit as x tends to 0, we do get a 0 term, so we have now the integral from 0 to pi by 4 of x times the cotangent of x plus y dx dy. And now once again using the linearity of the integration operator, we have pi by 4 times integral 0 to pi by 4 of log sine of pi by 4 plus y minus the double integral from 0 to pi by 4 and 0 to pi by 4 of x times the cotangent of x plus y dx dy. Now for this integral, let's introduce a phase shift going from the x realm to the pi by 4 minus x realm, or in this case the y realm, that is, so pi by 4 minus y. This means that we have pi by 4 times the integral from 0 to pi by 4 of log sine of pi by 4 plus pi by 4 minus y. In other words, we have log sine pi by 2 minus y dy. Again, I forgot the differential element up here as well. And we know this thing will sort out to the cosine of y, so that means we have another integral from 0 to pi by 4 of log cosine y. Okay, cool. And for this integral here, we're going to switch up the order of the integration operators, and we now have integral 0 to pi by 4, integral 0 to pi by 4, x times cotangent x plus y dy dx. So because the x variable is being held constant with respect to the first integration, we can take it outside the integration with respect to y operator, and this is what we have left. Now, the cotangent function does have an antiderivative, that's log sine. So that means we have pi by 4 times the integral from 0 to pi by 4 of log cosine y dy, or x whatever, we can just rename the dummy variable to whatever we want. Integral 0 to pi by 4 x times log sine again, x plus y. The limits for the y variable are 0 and pi by 4. Okay, cool. So let's just expand on this integral a little bit more. We would have integral 0 to pi by 4 x times log pi by 4 plus x, correct? Okay, minus log sine, again, I keep forgetting the sine function, log sine pi by 4 plus x minus log sine x. And again, using the linearity of the integration operator, we will have an integral from 0 to pi by 4 of x times log sine pi by 4 plus x dx minus integral 0 to pi by 4 of x times log sine x dx. And now I want to focus my attention on this integral by using another phase shift here from the x realm to, again, the pi by 4 minus x realm. So lots of transformations involved here, but it's getting pretty interesting. We have integral 0 to pi by 4 minus x times log sine, again, you can verify we would get pi by 2 minus x, and my screen just, yeah, I can really turn off auto rotate. Where to go? I can't find it. There it is, right in front of me. Anyway, so I have log sine, no, now it's going to be sine pi by 2 minus x right after the phase shift. So we have log cosine of x. Okay, cool. dx minus integral 0 to pi by 4 x times log sine x dx. And now, once again, one last simplification will give us pi by 4 times the integral from 0 to pi by 4 of log cosine x. I remember we had one term like that. We got one term like that earlier, so there must be some kind of cancellation. Minus integral 0 to pi by 4 of x times log cosine x dx minus integral 0 to pi by 4 of x times log sine x, again, terribly sorry about the sine x dx. I think we've done a pretty good job so far, and now it's time to at least piece everything together for the integral I sub 1, and then we can get back to the target integral I. First up, notice that we have a negative sign here, which is quite useful because it means that this thing and this thing cancel out. And that means I sub 1 just results in the sum of these two integrals. Now, what about the target integral I? Well, I forgot about that. What did it equal? Well, it was something up here. Yeah, so that was going to be I sub 1. We have its result. It's the sum of those two integrals, x log sine and x log cosine, minus pi by 2 times, there is a surviving integral 0 to pi by 4 of log cosine x, which is, of course, quite encouraging. So that's with a negative sign. Okay, cool. So that means the target integral I equals the integral from 0 to pi by 4 of x times log cosine x dx, plus the integral from 0 to pi by 4 of x times log sine x dx, minus pi by 2 times the integral from 0 to pi by 4 of log cosine x dx. And how on earth are we going to solve all three integrals? Well, they all have a very similar solution development and pretty much the exact same strategy. So I'm just going to solve this one here that I'm going to call, for reference purposes, I sub 2. And to solve these integrals, we're going to make use of a very cool infinite series expansion. Well, there are a couple of them, actually, one for the sine and one for the cosine functions. Specifically, they're logarithms. So for I sub 2, we're going to make use of log cosine x, which can be expanded as negative log 2, plus the sum over, terribly sorry about that, the sum over the positive integers k of negative 1 to the k plus 1 divided by k times cosine 2kx. Link in the description below for a proof on my Instagram as well as a video proof on YouTube. Okay, cool. So all we have to do here is multiply by x. And that means we just need to now integrate from 0 to pi by 4, which would give us on the right-hand side negative log 2 times the integral from 0 to pi by 4 of x dx. And switching up the integration and summation operators altogether, we have the sum over k of negative 1 to the k plus 1 divided by k times the integral from 0 to pi by 4 of x times cosine 2kx dx. And to solve this, all we need is some integration by parts. So we differentiate the x function here and integrate cosine 2kx. So a couple of derivatives, a couple of differentiations is all we need. And we have these alternating plus and minus signs. On integration, we have sine 2kx divided by 2k, and then negative cosine 2kx divided by 4k squared. Here are how the terms are paired up, which means that the integral I sub 2 equals, first up we have this integral of x, right? So that would be x squared by 2. We have negative log 2, x squared by 2, 0 and pi by 4. So we would have pi squared by 16, correct? No, pi squared by 32, rather, because of the factor of 2. So it's negative log 2 times pi squared by 32. Then we have a plus sign, then the sum, plus the sum over k of negative 1 to the k plus 1 divided by k times a bunch of terms. Let me just give myself some writing space. Much better. And we're left with x times sine of 2kx divided by 2k, with the limits being 0 and pi by 4, plus sine, then we have cosine 2kx divided by 4k squared, again with the limits being 0 and pi by 4. For the first term, we have in the limit as x tends to 0, 0, whereas for x going to pi by 4, we have pi by 8k times the sine of k times pi by 2. Okay, that requires some further analysis. And we also have a plus sign here, cosine of, again, k times pi by 2 divided by 4k squared minus cosine 0 is 1, right? So we have 1 by 4k squared again. And now multiplying the negative 1 to the k plus 1 term, we get negative pi squared by 32 log 2 plus the sum over k. And of course, we're also making use of the linearity of the summation operator. So we would get, wait a minute, we would get pi by 8 times the sum over k of -1 to the k plus 1 times sine of k pi by 2 divided by k squared, plus we also have this sum over k of cosine k pi by 2 times, again, wait, I forgot the -1 term. Oh, dear me. Oh, wait, that was not what I was supposed to do. I was just supposed to move this to the side. And I have -1 to the k plus 1 divided by, now it's going to be a factor of 1 by 4 outside, and we have k cubed here, minus the sum over k of -1 to the k plus 1 divided by k cubed, again with a factor of a quarter outside. Now, these k pi by 2 terms are pretty interesting for both the sine and the cosine functions. If we take a look at the sine function, sine of k pi by 2 is, well, 0 whenever we have an even value of k. And it's equal to, let me see, for k equal to 1, we have sine pi by 2, which is 1. So it should be -1 to the k plus 1 or k minus 1, whatever, it means the same thing, for odd k. Okay, cool. So that's all fine, which means for the first sum, what we need is a transformation. We only need k of the form 2n minus 1. So those are all the odd integers, and the sum will start at n equal to 1. Okay, cool. So this implies that I sub 2 equals -pi squared by 32 times log 2 plus pi by 8 times the sum over the positive integers n now of -1 to k is being replaced by 2n minus 1. So we have 2n minus 1 plus 1, which is, of course, -1 to the 2n, which is 1. And we have sine function here giving us -1 to the, yeah, it's -1 to the n minus 1, correct? Yeah, that sounds about right. Sine of 2n minus 1 times pi by 2. Yep, that's it. Divided by k squared. Now, k squared is now 2n minus 1 squared. And this is pretty good because we now have the series expansion for Kaplan's constant. Now, what about the cosine term later? Well, we have a quarter, and we have the sum over, whenever k here is odd, then we have cosine being 0. So we need k here to be even. So k here equals 2n, and again starting at 1. So the sum runs from 1 to infinity of cosine of n times pi. And cosine of n times pi would be -1 to the n, correct? Yeah, it's -1 to the n, cosine pi -1. We also already had a -1 to the k plus 1, k here being 2n, so we have 2n plus 1, which means we are going to have a negative sign. So let me just write this one over here. Divided by, what exactly do we have? We have 8k cubed. Then finally, we do not have to do anything with this infinite series here. This is perfectly cool. It's the sum from k equals 1 to infinity of -1 to the k plus 1 divided by k cubed. So putting everything together, we have -pi squared by 32 log 2 plus pi by 8 times, this thing here is Kaplan's constant, the original top g, minus a quarter of, wait a minute, that's -1 to the n. And wait, this was supposed to be n cubed. Terribly sorry about that. And we have 1 by 32, and we could use an extra -1 or one less -1. Again, same thing. So what we have here is the Dirichlet eta function evaluated at 3 minus a quarter of the Dirichlet eta function, again evaluated at 3. So what is 1 by 32 minus a quarter plus a quarter? I'm really bad with math. That should be, wait, there was a plus sign over here that I made an adjustment for. So yeah, now I need 1 by 32 minus a quarter. So -7 by 32. Okay, cool. This is going to be negative 7 by 32 times eta 3. And now translating this into zeta 3, we have negative 7 by 32 times 1 minus 2 to the 1 minus the argument here is 3 times zeta 3. So we have 1 minus a quarter, which is supposed to be 3/4 if my memory serves right. So that's negative 21 by, what's 32 times 4? Why is all the hard mathematics inside this video? So we have negative 21 by 128 zeta 3. So that's the hard bit of the video done. Prior to that was extremely easy, and now everything that follows should be extremely easy as well. And let me just write the result now. We have I sub 1 equal to a lot of stuff. That is actually a very beautiful integration result in itself. We have pi squared by 32 times log 2 plus pi by 8 times Catalan's constant minus 21 by 128 times Apéry's constant. That's zeta 3. And all we have to do is rinse and repeat the process for I sub 2. That's the integral of x times log sine x. And this is I sub 3, the integral of log cosine x, including the negative pi by 2 term being multiplied by it. So I included that in the results. So all we have to do now is just add these terms together. And immediately we see some really nice cancellation here. We've lost Catalan's constant, but we've regained it as well. So that's pretty cool. I'll write that straight away, that I equals, wait, we have Apéry's constant as well. That's 14 by 128. Again, this should be 7 by 64. Zeta 3 minus pi by 4 times Catalan's constant. Then you have, what exactly do we have? Negative pi squared by 32. Negative pi squared by 32. That's negative pi squared by 16. Then you already have pi squared by 8. So that's 1 minus 1/2 kind of thing, which gives us 1/2. So we have plus pi squared by 16 log 2. And this was a really epic integral. It required lots of transformations, series expansions, some integration by parts, work with symmetry. This was really cool, and the result is definitely worth it. We have Apéry's constant, and we have Catalan's constant, and as well as log 2. I mean, log 2 never really hurts, right? I hope you enjoyed the video. I hope you learned something from the video. Do drop me a follow on Instagram as well. Be sure to like and subscribe, and in case you like the effort I'm putting out, especially this kind of effort, then do consider supporting me on Patreon. Thank you. See you next time.